Hello there. So, on this episode 3, or the third part in this series of building a circuit that we're calling, which is the Twinkle circuit. At this point, we should already have our stock take done, as you see by I have my stock take over here in this Word document. Well, the notepad, yours will be in a better location. What we're going to be doing today, well, this lesson, we're going to be reading circuit diagrams, understanding what part relates to what in our circuit. Then we're going to be placing some of the components onto the board, and we're going to be preparing to solder. Now, I'm going to do 2 episodes back to back as I'm recording it over here, but I will divide up into 2 different episodes to allow some students that only want to see the tutorial for how to solder, and so they can redo that video so they don't have to look through this video. It might just be too long if it's a single episode. I'm not sure. I'm still working with this. I've already taken some feedback from students. For number one, we Fresh Prince of Bel-Aired this setup by rotating it to be in the correct location now. So you're seeing the screen in the same shape I am. You should be seeing like the words in the correct order. It's all a improving process. And so I think we're ready to go. So over here I have this circuit board diagram. Now, sometimes when you buy a circuit from like AliExpress or those online retailers, they might give you, if you're lucky, they will give you a circuit diagram. And even if you're more lucky, the diagram will actually have English or Arabic numerals on it, so you can relate to your circuit board what components they are. This one over here is just using my knowledge and experience from looking at the circuit online. I knew that this was the right, circuit diagram for the one we're doing here. So let's look. Let me just adjust this screen up slightly so we can see some more stuff as I'm on. Okay, so if we look by my circuit, which is where's the camera? There you go. So if we look by the circuit over here, we should see that it already has some letters and numbers relating to, I love autofocus. It already has some letters or numbers, and we can see that these things do relate to things that are on our circuit. For example, we see that R1 on our circuit board relates to the R1. Let me see. Let's go full pro streaming setup and say relates to the R1 over here. And we can see there on this board it was 10K, and on the circuit diagram it's 10K. And that's what I used to look through the internet and find a circuit diagram that I thought was accurate. Now we are lucky that in most parts of our circuit, give me a second to just fix this up some more. There, I'll remember to adjust that more later. So we are lucky with our circuit that most of the components are labeled to what they are. For example, let's look at the tiny camera over here. That might be easier. There we go. So if we see like R1 is clearly labeled as 10K. So I wouldn't need to refer to the circuit diagram to put down my 10K resistor because it's written down there. Same with the 470 and so forth. The issues we have is like these capacitors. Now, there's only one type of capacitor, so it's not the largest bit of difficulty because we're just going to solder in our 3 capacitors. But we see they are still labeled C1, C2, C3. The issue we have is if we wanted to build this circuit from scratch, let's say we just had this circuit board and we wanted to build it with components in the workshop, or we had to replace, a component, we wouldn't know which size capacitor we would have to put into that spot. Now, lucky we did our stock take, so we could find that out. This is where we would relate it to the circuit diagram. So if we look at what do we have? We have C1. C1 on our circuit diagram is, C1 is over here, and C1 is our 47 microfarads, which we already know because we did our stock take that is the exact same value. Where are you? That is the same value of 47. So again, that's another way I checked to make sure this is the right circuit. But this is the 47 microfarads capacitor. So good, so we know we can relate this up. So if we didn't have the circuits, if we didn't have the components for the circuit, we could use a circuit diagram and we could get another 47 microfarads capacitor. But interestingly, it doesn't have the voltage. If we remember from last tutorial, we were saying that the voltage limitation on the capacitor, this one over here is the 25 volts. The 25 volts is just what the maximum voltage the capacitor can handle. And so notice this circuit here, it doesn't say that. It doesn't say it's a 25 volts. Now, for the most part, it's fine, because like we can just put in any, we know that our maximum voltage in our circuit is 12 volts. Note, this is a slight thing that's different between this one. This diagram says 3 to 12 volts, while our circuit diagram over here says 2 to 12 volts. Look, I don't know how much of a difference. It shouldn't make that much of a difference, but we can plug it up to 3 volts anyway. Usually they always give themselves margin for errors, and it's going to relate to like that 5% accuracy rating that all our components have and individual parts. But for the most part, 12 volts is the maximum voltage that they're putting here, which is the more important one, because that resistor that we have is related to like how light those LED lights are going to shine. Anyway, we're going down to 12 volts, up to 12 volts, and 12 volts is below the 25 volts of these electrolytic capacitors, so that's going to be fine. And in the diagram, they don't bother saying that they're 25 volts because you can put in any other voltage capacitor. Now, when you see a more complicated circuit, especially a circuit that has particular components that are of high voltage, let's say, for example, like a power supply for either like anything from a TV to a computer. On one end of the power supply, you're dealing with mains power voltage, which is 230 to 240 volts. So if you have capacitors on that side, your capacitors will have to handle 240 volts or more. But then on the other side of the power supply, where you're powering up, for example, a computer, most of your voltage is plus or minus 5 volts, plus or minus 3 volts, or plus or minus 12 volts. And so you wouldn't need the 240 volt capacitors. You can get the smaller 25 volt capacitors to cover that. And that would be mentioned in the circuit diagram. They'll do some sort of reference to these lines over here are going to be high voltage. And it is something that you as an electrical engineer, like if you become one, you would have to determine that this line over here, if we follow this line over here, this line connected to this capacitor will be at around 12 volts. So I need a capacitor that is able to handle the 12 volts. Okay, so we have that information, that's good. Same with our resistors, our resistor numbers all match up. Our LEDs match up with all their lights as well, all that is great. Right, and we know all these. Now, the reason why you want this diagram and why it's important is when it comes to our transistors. Now, we remember from last lesson, looking at the main screen here, that we have 9 13s, we have 2 of those, and we have one 805. When we look at our circuit board, now the actual components themselves, these transistors, are going to be registered as a V. So as you see over here, up here we have V1, and then we have V2, and just below it over here we have V3. Now there is no indication here on the board of which transistor goes in which location. So that's going to be very relevant. In this particular circuit, I don't think it actually matters which, like, it just means the lights are going to flash in a different order. So in the grand scheme of things for this one, it doesn't matter. But when you get to more complicated circuits, where especially these transistors feed into each other, it is very important that you get them in the right order. And so that's why we look at this circuit diagram over here, and we can see here that they've actually have the numbers labeled. So V1 is 9013, V2 is 9013, and sorry, V1 is 9013, V2 is 9013, and V3 is 8050. So when we are putting it in our circuit here, we know that this last one over here down the bottom is going to be our 8050. And again, to minimize any mistakes I make, I'm going to write that down on my handy little sheet here. Now, if you were doing your stock take, well, obviously you're doing your stock take, but when you do your stock take, it could also be helpful for you to write down these components on your stock take. So if we look at your stock take up here, We have our components over here. You can make a new category. Code. Well, we can make it our code there, or you can you can't see that on my screen because of that sizing is a bit out. That's probably better. So if we have our code, and when we come down to, we can get our code for all our components, but let's just put these two for now. So we can say v1 and v2. So later when we're referring to our stock take, we can, now we have a, a paper trail of where the individual components go. This could also be very, when we get to a more complicated circuit, you probably want to do this with all your resistors as well. Label them. For example, the easiest one we can have here is like the LED lights. We can say the LED lights are all the L's, and they actually range from L, we can say 1 to 12, and so we know that on our circuit that all our LED lights are coded 1 to 12, and it looks like with our resistors they're annoyingly 1, 3, and 5, so all the odd ones are the 10Ks, so are 1, 3, 5, and then over here we can do 2, 4, 6, and because I love consistency, I'm going to change that to V1, V2, and I don't think, the capacitors are the C1s, so C1, 2, 3. So right now we're having like a coding. Yeah. Right now we have like a coding setup. So if there's any problems when I have to replace parts, I don't have to look at my circuit board now. Again, this is relevant because when we see over here, this particular resistor, right? Let's say this resistor is over here, and when I put my resistor in, it's going to cover that spot of the 470. Now we built this system, we know it, but when we think about the world of consumer electronics, I'm going to make this thing in a factory somewhere, or even like in a workshop, and then I'm going to send out, it's going to be sold, and this thing could be used 10 years down the line. And firstly, the actual material could be rubbed off just from wear and tear, but also the resistor itself is on top of the circuit board, and that might break. Sorry, not might break. It might be covering up the numbers, and so we can't rely on reading the circuit board to find that out. And if you actually see any videos online of like resistors or stuff, like over years and times, it has broken down. Sometimes it can explode and make dark marks on the circuit board, and so it's going to be hard to read. And this is where they would be relying on these original circuit board diagrams, or like as we're doing our stock take, that's like the more basic version of parts that are required. They will use that to determine what parts have to be replaced. Okay, so that is our how to read the circuit diagrams, and we have all our individual components. With the last part about the components that I want to talk about is the LED lights over here. Right, it uses the circuit diagram for the LED lights, and so we have the triangle, the standard LED triangle with the line. So this symbol over here, that is just the triangle with the line, that represents a diode. Right, it represents that current can only flow in one direction going through there. It will not work in the other direction. It's these arrows over here that represent they're like light escaping out of it, which that's the difference between an LED, because LED stands for a light emitting diode, and so that's saying that the current has to flow in this direction, but then it will also produce light if there's current flowing through it. So it's telling us the orientation of the LED light in this scenario. Which means this over here, this is going to be our plus, and this over here is going to be our negative. Okay, so we know that. Other things, we have the same scenario. We have the same scenario with these capacitors. We have the plus side over here. So we know that in our circuit, our plus is our longer leg, and this over here would then have to be the minus, which is also the part where there's the white marks on our capacitors, so we can line them up. Circuit diagrams in general. we have these lines and they're connecting all our components. Now we already know that this is the symbol of a resistor, that's a symbol of a electrolytic capacitor. This over here is one of the symbols that we can use for, this is not a battery pack per se, this is just a power source. Because we'll know that a battery pack will have the, will have like some sort of indication. No, let me do it a bit thicker, please. Let's do, why not orange? Okay, so a battery pack will have a shape that looks like this, right? Representing that would be the positive end, and this, that will be the positive end, and this will be the negative end. This over here is just showing that it's some sort of DC power. So it's saying battery pack's not included into the circuit. It's just saying you need to provide 3 to 12 volts. That's why it just has this symbol of plus or minus. Other circuit diagrams could just have the sign there for positive and negative like that. That'll also be fine in most cases, in most simple cases. Where the circuits become more complicated is they don't necessarily have to put the negative sign there. A circuit diagram could, let me just move this slightly to the side. There we go. A circuit diagram could, instead of a negative, could have a cable coming out here, and it could have a sign that looks like this. Right, this is a sign that represents our grounding, and so in most circuits, the grounding is like the lowest level of voltage. And as you remember, our voltage is a potential, so a difference between two voltages. This plus or minus means that over here on this side of the circuit is actually 12 volts, and over here they say it's 0, but that's not. We say that's just the potential difference between those two sources. In reality, this could be 112 volts over here. So that could be 112 volts over here. And all it means is on the negative side, it just has to be 100, because that difference is still 12 volts. So what we have by this symbol over here, this means ground. Ground means that the negative is going to be equal to 0. And they can often use this in circuits because as the circuits become more complicated, it's going to be difficult to draw like a wire that connects all the way back to the original of the circuit. You could in theory have a thing that comes out here and say that that's our sign over there for our negative. Let me go a bit lower. There we go. That could be our sign over there for our grounding, and so I wouldn't have to draw this cable coming all the way back. This circuit's not that complicated as a drawing, but as you get to more complicated circuits, it really helps you communicate effectively where like the negative of a circuit is. All right, next thing with circuit diagrams. We have lines over here. All right, so that makes sense. Lines are equivalent to our cables. Wherever you see this, let me show you a difference. So we have this point over here, and we have this point over here. These are parts of the circuit that are not, they don't mean the same thing. Because this over here has a dot on it, that means that that is physically a connection. So this wire over here on top of L9 is connected to this cable up here. So that, yeah, so it's physically connected to that. Over here, this cross section, because it is not, it is like two wires that are like over each other. That means that they just had to draw it in that way. So we have to keep in mind that if we had to replicate this circuit for whatever reasons, like if we wanted to do it on prototyping board or we're going to make our own circuit, that these two wires do not actually touch. So we have to find a way to do that in the circuit. So when you do make them touch, they do have a dot. The last thing is this over here is the image of the transistor. So it's, yeah, that shape, electrolytic, and I believe that's everything. I think that's everything for the circuit. I'm just going to move it slightly more to the side now so we don't have to see it. Alright, so with that information, let's start by let me just rearrange the screen setup now so I have the right amount of zoom. Yeah, we'll go with that. Alright, so let's start loading up our circuit. I'm going to put this, no, oh, no. Okay. So let's start loading up our circuit with some parts. Now, how you want to start the circuit? The It's ultimately up to you how you want to line up your circuit. I like doing the easiest components first. Um, I would always pick the, sorry, not the easiest components. I would always pick the components that it's going to be easier to solder them when there's no other components in there. Usually, if you have an IC chip, which is like one of the ones that have like multiple prongs sticking out, you want to do them first because they usually have smaller points and stuff, and it's going to be difficult to get your soldering iron around the location to do them. Also, if your circuit has any surface mount components, so these are all through-hole components because they have like cables, but if there's any surface mount components, you want to do those first because they require you to have very, very close access to the circuit board itself. So let's start loading up. We're just going to put everything through it now, and then we'll deal with soldering. So over here, these are my 10K resistors. These are my 10K resistors as we've done before. I'm just pre-bending them approximately with my fingers. Just giving them some sort of a bend like that. And when I'm putting them in, I'm sticking it in one foot at a time, making it fairly loose, and it just slides down because these are very, very thin resistors compared to the... I wish I know where the autofocus point was. Anyway, so they're in there. And then what I want to do is, because if I leave it like this, it's just going to fall out, right? Because it's very loose. Let me, I don't think we need this as big anymore because we will be referring to it. But so as we have this piece here, it's actually very loose and it'll fall out if you it'll fall out fairly easily. So what I like to do when I put my resistor in there, I stick it through and I just bend the legs. Where are we there? I bend the legs slightly out. So the resistor now, right, it is not falling out because of the legs are stuck out. And I'm going to do that for now all of my, I'm going to do that for all of my 10K resistors. So that over there is resistor number 3. Let's plug in resistor number 2. If you want your resistors to look pretty, you can put the colors in the same order, but a resistor is a non-polarized component, so the direction does not matter. It's all about how you want your circuit to look. When it comes to actually soldering your resistors and other components, neatness actually doesn't necessarily make a circuit perform any better, but what it does do is it does allow you to find any problems with your circuit better. If you have all your resistors, like here I have all my resistors lined down and they're all flat, right? So the resistors are the most passive part of your circuit. It's the part where they're least likely to have problems. But if they're all nice and flat, I know that they're definitely all going to be in line, they're all going to be soldered, and I can cut them all down, and they're going to be out of the way of other components. When we get to more complicated components like these transistors that have 3 legs, or 3 prongs, they're going to be more difficult to put in, and depending on how we put them in, they're going to not solder right, and they might not be connected to the circuit, which might cause some additional problems. So me in general, I like to get my components down. When it does matter, the height, it matters for things like these LED lights. Because when we put them into the system, right, so as we mentioned before, the shorter leg goes, or the flat side of the LED, the flat side of the LED matches up with the flat side. Where's my pen? There we go. The flat side of the LED is matching with the flat side on the board. When I'm putting in my LED light, I can go all the way. I can either go all the way down to the base. Oof, doesn't like that. I can go all the way down to the base, and I can go flat onto the board. Right, that is one of the options you can do, and sometimes you see LED components and they do that. The other option is LED lights. Some of them have this little marking over here. They have some sort of marking on it. Um, you can solder your light up to that, and that means they'll all be the exact same height. And it sometimes gives the solder, it sometimes gives it extra support, and you can do that. You can also do it at a much higher height. Now, where the higher height is relevant is this over here is just this is just a circuit component, and when it's built, it's going to look essentially, well, it's not going to look like this circuit. This is another circuit that you've done, but we can see this is a completed circuit. This is great for us to test with, and the lights are fine, but this is not a consumer product. When you buy a consumer product, it usually comes in some sort of housing. So like this device over here, which is another thing that was bought from AliExpress, and I can tell that because like some things are incorrect on it, like they used the wrong type of screws. But regardless, we have a device over here, and we see this LED light is soldered right to the surface. Of course, you're at the angle where I can't see. There we go. That LED light is soldered right to the surface. Now, that's fine in this particular device because it's see-through, but let me just grab the camera and show you another device that has an LED light. So over here we have the soldering iron. So I'm just going to turn it on just so we can see the light. All right, the soldering iron. Are you going to turn on? Yep. The soldering iron has an LED light. Now this circuit, the circuit board for the soldering iron doesn't, if it had a circuit board right behind it, right, that LED light would be fine. But depending on how you're designing the circuit, you might not have the LED light right up against the circuit. Like there might be limitations in your design that would prevent that. So in that case, you'd have to have some sort of height on your component. We'll deal more to this later as you do like other tasks like where we make consumer electronics. And we'll have to worry about design details like that. It's also relevant for like switches. You want them to be accessible. For example, like potentiometers. As you see by the soldering iron, it had a potentiometer as well. That is usually screwed to a component. If you have things such as audio jacks or plugs, these are all things that are probably raised or they're not like directly onto the circuit board. So we would adjust that depending on our components. So, but apart from digressing too much, this particular circuit, you can have your LED lights in whichever way you desire, because this is a novelty thing just showing off electrical lights, so we can worry about that. With the capacitors, they go in, as we already mentioned from the other video. With the capacitor, we have the white side of the capacitor, right, lining up with the white mark on the circuit board, and then we can put those in. Now, the capacitors themselves, they're actually we have to actually force them to have them straight onto the bottom because the holes through the circuit boards are slightly wider than the width of the capacitor. Now, this width between the 2 feet of the capacitor are not uniform. Right? Every manufacturer can do them slightly different. It's based on like how they roll their material. So we don't have to actually have the capacitor fully flush, but have it like, I would like have it as low as I can without putting too much force onto the capacitor. Again, you don't want to force the component to break. We have our capacitor, and then the last of the interesting parts is our transistors. I'm looking. This is just to confirm. This is a 9. This is the 9 one. Can we see it? Ooh, let's get some light. There we go. The 9013 is a particular one here. And so when we put this in, we know that through our database, through our stock take, we said that that is a V1. So when we're putting in this particular component over here, so let's just look at this lineup over here. This is the feet. Notice how the feet of it are not, they don't directly align up with these holes. In fact, the holes themselves are, they're too far apart. So we have to pre-bend the feet of this transistor to fit it inside these holes. Now I just like to pre-bend the feet and then like just wiggle the way in of like doing it one at a time. You may need to bend it with like, I doubt you have to bend it with pliers, but you just got to like slowly work it in. Right, and then once you have it in, great. So again, like the LEDs, this has a flat side, and there's a flat side on the circuit diagram. Now, they're trying to be confusing here. Look at this one has the flat side on, I believe that's your right, but the other two, which is this one and this one, have the flat side on the other side. So don't get confused with that. It's trying to trick you and bait you into doing something incorrect. So we have the transistor in here. Like how low we have the transistor, because unlike the capacitor, this is actually very, oh, that's a good view over there actually. Do we see how far away those prongs are? Like as I start pushing it down further than that, it's going to start to cause problems, and it could potentially, if it's like a low quality piece of metal here, it could actually break at the feet. It could actually break at the feet, so we don't actually want to push it too far. I would, once it's in a position where it's safely secure and it's not like going anywhere, I would be happy with that height of the transistor. It also means this, in this particular circuit, I can know from experience, the transistor is going to be the hardest part to solder and where the most problems are going to happen, because it's the most sensitive to heat, and our students find the very small proximity of soldering those components together cause some issues. So I like to give myself a bit of extra height there, or I recommend students to give themselves a bit of extra height when they're soldering the transistor. I'm just going to pull these things off, so because I'm going to need them for the next tutorial. The last part that you'll be soldering into your circuit once you've done everything will be these terminals. So I put them in here. Now these are actually they're actually the thickest component in your kit, in the sense of if we look at them, we see how they're actually like a thicker piece of material than other things. So obviously thicker pieces of metal find it harder to bend, so it's really difficult to bend this, and I wouldn't actually recommend bending it at all. The issue you're going to have is when you're soldering them, is it's very easily going to fall out. So we have to find a way when we're soldering this. We might have to do some dexterous hand positions where we have it hold it up like this, or we can have our circuit, if we have it lying against the ground, we can solder it in. And actually for that reason, when we go to the soldering for the next tutorial, I might actually just do this one before the resistors, because when we're worrying about the ordering of soldering, like we said, we wanted to do the surface mount components first. Then you want to do your components, if you have a choice, always do the components in order of height. So we do the lowest ones first. The advantage of doing the lowest one first, so let's say if it's the resistors, if you do the lowest resistors first, we can flip the circuit over and we can use the gravity and this weight of the circuit. We can use the gravity and the weight of the circuit to hold the components in place. If I wanted to do that particular component, the terminal ends, and let me just put a capacitor in over here, and I had a capacitor in, I couldn't easily rest it against the ground because the capacitors would be the highest component, and it would cause some angled problems with my circuit, depending on what device I'm doing. So I'm actually probably going to solder this in after I do my resistors in the next tutorial, where we'll be learning how to solder. All right, I'm going to go set it up now, and that will be uploaded soon.